Okay, this is hour 2 of Physics 1B for November 9th. We're going to start off by looking at a problem involving a heat engine. So, here is the problem. A gasoline truck engine takes in 10,000 joules of heat and delivers 2,000 joules of mechanical work per cycle. The heat is obtained by burning gasoline with a heat of combustion equal to 5 times 10 to the 4 joules per gram. We would answer all these questions. What's the thermal efficiency of this engine? How much heat is discarded each cycle? If the engine goes through 25 cycles per second, what is its power output in watts, as well as horsepower? And then how much gasoline is burned in each cycle, and how much gasoline is burned per second and per hour. All right, so let's kind of draw like this one of these heat diagrams for this. So it says it takes in 10,000 joules of heat and delivers 2,000 joules of mechanical work per cycle. Right? So in terms of the picture that we drew earlier, if we try to make it somewhat similar, we start off with 10,000 joules. That is the heat that comes in. And of that, about 1/5 of it, or 2,000 joules, so if we divide this up into fifths, something like this comes out. It needs to be the same size the whole way. Something like this. So we've got 2,000 joules of work that's coming out. And the first question is, what is the thermal efficiency of this engine? So how do I figure that out? How do I find what its thermal efficiency is? If you look back through what we talked about over the last hour, what do you see? How do I find the efficiency based on these two numbers? The heat that comes in and...
Oh, it's just the work divided by the heat.
That's right. Very simple. The efficiency is just equal to the work done by the engine divided by the heat that comes in. So in this case, that's going to be 2,000 joules of work divided by 10,000 joules of heat. So 2 over 10, which would be about 20%. Or 0.2. This is going to give you 0.2, which is 20%. Okay. Pretty simple. Part B, how much heat is discarded per cycle? So the heat discarded would be this. Right? And we had a relationship that we wrote down earlier, which was that the work done by the engine was equal to the difference in the heat plus, it's basically the heat in plus the heat out, where the heat out is often negative. So for solving this for QC, you get QC is equal to W minus QH, and that would be equal to, what is it, 2,000 minus 10,000, one extra 0, so that's going to be equal to negative 8,000. So this is, you could think of the heat that goes into the cold reservoir, right? This is like effectively the heat that's lost every single cycle, because it doesn't turn into work, and we don't really get it back in any way. So it's kind of like the amount of heat lost per cycle. And it says how much heat is dissipated. Negative 8,000 just means that it goes out of the system. You could write it as a positive number if you want, if you say it's 8,000 out or something like that, if that makes more sense to you. Okay. Part C. If the engine goes through 25 cycles per second, what is its power output in watts? So it goes through 25 cycles per second. Now what does this mean to y'all? If it says power output, do we want the 8? This ends up being 8,000 we calculated, right? So do we want this number or do we want this number to figure out the power output of the engine? Or do you want this number? Yeah, the work, I would agree. So the work done by the engine each cycle is 2,000 joules. So if it goes through 25 cycles per second, we can say that it does 25 times 2,000 every second, right? So if we do 25 cycles per second, and we multiply by the number of joules per cycle, which is 2,000 joules per cycle, then that should give us joules per second, which would be the power out of the engine. So 2,000 times 25 would be like 50,000 watts. Is it 50,000? Okay. And joules per second is watts. All right, part D. Oh, they want it in horsepower too. Okay. To get from horsepower to watts, I think that 746 watts is equal to 1 horsepower. If one of you could go look this up on the internet real quick and tell me if that's right or not, or look it up in your book, either way. Pretty sure that's correct. So then if we take 50,000 watts and we divide by 746 watt per 1 horsepower, we should get the answer in horsepower. Did anyone look that up? Is that right? Is that what you're answering, Dawes? Okay. So 50,000 divided by 746. So you get 67 horsepower. Okay. Be sure to check that and make sure you don't get a different answer. That seems reasonable, though. Because 70 times 7 is about 49,000, so yeah. Part D. How much gasoline is burned each cycle? They gave us this. They gave us the heat of combustion. So, given that we know that there's, 2,000 joules of work being done, this is per cycle, right? So the work is 2,000 joules. And that work is basically coming from wait a second. It says how much gasoline is burned each cycle. What should we use for the gasoline burned each cycle? The 10,000, yeah, I agree. So for this, we want to use the amount of energy that comes in. Because the energy that's coming into the system, this energy is coming from... this energy right here is coming from gasoline being burned. So we want to use 10,000. So we take... here, let's write it like this. So QH should be equal to the latent heat of combustion multiplied by the mass that's burned. So we can use that to solve for the mass. The mass is going to be equal to QH divided by LC. So QH is 10,000 joules. And we're dividing that by LC, which is 5 times 10 to the 4. Joules per gram.
5 times, that's like 1 times 10 to the 4 over 5 times 10 to the 4, so it's going to be like 0.2 grams. That's weird. Y'all agree? 0.2 grams per cycle? And then it says how much gasoline is burned per second and then per hour. So for that, we know that there's 25 cycles per second. And we multiply that times 0.2 grams per cycle. So every 5 cycles it burns 1 gram. So 25 times 0.2 is 1 over 5. It's just 5, right? 5 grams. 5 grams, cycle. 5 grams per second. And then if we want to get that in hours, we would take this and we'd multiply by 3,600 seconds in an hour. Is it 18,000? Or is it 1,800? 18,000, right? Yeah. Which would be equal to 18 kilograms. 18 kilograms sounds like a lot. I don't know how many liters of gasoline you need to get 18 kilograms. That would be like
40 pounds? It is a gasoline truck. Gasoline truck engine. So maybe, I don't know. I don't know if these numbers are realistic. They seem awfully, they're nice round numbers, which makes me think they're not realistic. But, you know, having nice round numbers makes it easy to do the calculations and easy to understand what's happening. Oh, this would be kilograms. This would be grams per hour. And this would be kilograms per hour, technically. But, yeah. Anyway, pretty easy. Anyone have any questions? Okay, so I haven't really looked at the problems in this chapter. I'm tempted to, because like I often feel like, especially with this textbook, University Physics, that the problems in the chapter are always like way easier than the homework problems. Do you guys want to do another problem that's like from the textbook that we just pick from random, maybe? What do y'all think about that? Would that be helpful? And then I let you all work on it for like 5 minutes or so. What do you think about that? Would that be helpful? Okay. All right, let's see if we can find one that we think that we can solve that will be a little more challenging. That seemed really easy. Maybe they're all really easy. I don't know. I don't remember these problems being particularly easy, though. Okay, so this is... We haven't talked about refrigerators yet, but we have... This is the chapter. This is we're on 20 points. Heat engines. Okay. What if we do this one that has a graph? Let's try this one. Okay, looking at 20.4, this one's not much harder than the one we did, actually. And this looks like exactly the same problem we did. So maybe I'll give a couple of these for your homework. But let's try this one. It's 2 dots, right? So that means it's a little more challenging. Here, let's put this into the thing. And then what I'll do is, let me copy paste this, and I'll put it into the chat, too. Because last time I was teaching 1C, people were saying this is helpful because they can't necessarily read it. So you can copy that if you want to from the chat. And then I'll copy it into OneNote as well. And then what we'll do is I'll give you 5 minutes or so. So let's see, 11:27. So take your time, read the problem. Well, let's read it together, and then I'll give us 5 minutes. Let's make sure we can actually do it. Make sure there's not something here that we haven't talked about yet. It says the PV diagram in figure E20.5 shows a cycle of heat engine that uses 0.25 moles of a gas with gamma equal to 1.4. Process is adiabatic. Process AB, it's saying. AB is adiabatic. Find the pressure of the gas at point A. How much heat enters this gas per cycle, and where does it happen? How much heat leaves the gas in a cycle, and where does it occur? This is weird. It looks a lot different than the one we did before because there's no like vertical line right here. Anyway, how much heat leaves the gas in a cycle, and then how much work does the engine do, and what's the thermal efficiency of the engine? Yeah, this one's quite a bit more challenging, I think, at least on the surface. Should I write down some of the equations? That might be helpful, right? So, comparing back to the problem we did earlier, I suspect that what you will need are things like, for a constant volume process, you've got N times CV times delta T. That's constant volume. And then the other equation we had was for adiabatic. It did say it, part of this was adiabatic, right? AB is adiabatic, yeah. There's two different equations we have. One is TV to the gamma minus 1 is constant. So that another way to write that is T1 V1 gamma to the minus 1 is equal to T2 V2 gamma minus 1, where 1 and 2 could be A, B, or C. And then there's one other version of this equation that involves pressure, right? So the pressure version, okay, I might have to go back and look because this stuff is all very new to me since it's the first time. I think it's PV to the gamma equals PV to the gamma. Does that look right to y'all? I think that's right. That would be from the last chapter. So this chapter, adiabatic processes. We did all this math. Yeah, that's right. That's right. Yep. Okay. And there's some other equations here. I feel like we might need this too. I'll keep those in the back pocket in case we need them, but you guys can always get access to them. Okay, so take 5 minutes. It's 11:25 now, so go until 11:30 and just do your best to try to solve this problem. You do not need to completely solve it. Just get as far as you can, and then we'll come back and we'll talk about it. I don't know. Do y'all think it's been 5 minutes? So we're gonna talk for a second, and then I'll give you more time. I think. You think we have to assume that this is an ideal gas? What do y'all think? Is that an acceptable assumption? It does say ideal. Okay. I was gonna say none of these equations work if it's not ideal, so you're right. Okay, that makes more sense. Do you need more time? I need more time because I had to stop and think about that for a second to make sure I didn't see that word. Let's take like another 4 or 5 minutes. Okay, so it's been about 12 minutes or so total. How are y'all doing? Did you guys get an answer to part A? What the pressure of the gas is at point A? You want to get that answer? Yeah, 12.3 atmospheres, I agree. And then what about part B? I feel like once you get A and B, the rest of the problem is really simple. What about part B? Did anyone get the answer for part B? We'll go through all these steps, by the way. I'm not going to skip over them. I just want to see where y'all are at in terms of solving it. Still working on B. Did anyone at all get an answer to part B? So, does anyone know how to find CV? So remember what we did last time? Like if you're given gamma, how you find the value of CV? Let me just write this down so that... So gamma, what is gamma equal to? You don't remember? CP over CV, right? And what is CP equal to? CV plus R, that's exactly right. So this allows you, if you combine these together here, gamma equal to, you plug in CV plus R, and since you know R, you can solve this to get CV, right? Because this would be equal to 1 plus R over CV. So there you go. You know what R is? It's 8.31, and gamma is 1.4. Okay, does that help? Okay. Give you a few more minutes. Okay, did anyone get an answer for Q yet? For the heat, QH, I guess you'd call it, the heat that enters for part B. That is very close to what I got. It's probably just rounding or something like that. Yeah, I got 5465. So we both agree that it's about 5,500 joules, basically. And considering the number of calculations you have to do to get there, that makes sense. Okay, if that's the case, did anybody else get something similar? Mine could be wrong, too. I could have just written something down wrong somewhere. I could have entered something in wrong, too. Anyone else get something close to that, like 5,500 joules for part B? This is a pretty difficult problem, 5474, so pretty close. Yeah, that's much closer to his than mine was, for sure. All right, I think that's enough that we can kind of go through and solve it. I think that if I gave you all another, 15 minutes, probably, I bet everybody could finish solving everything, but I do want to talk about refrigerators and the Carnot engine and the second law today, so let's try to solve these parts. All right, so part A, find the pressure of the gas at point A. All right, that part seemed like to not cause people many troubles. The pressure of the gas at point A, I believe we end up using that equation right there. At least that's what I did. I don't know if there's another way to do it. If someone else came up with another way, let me know. According to that equation right there, if we do some manipulation, the pressure of the gas at point A should be equal to the pressure of the gas. It's an adiabatic process, right? So it says in the problem that this process right here is adiabatic from A to B. So we need to use the pressure at A and the pressure at B. So we would say pressure at A is equal to pressure at B multiplied by the volume at point B divided by the volume at point A. And then we just raise both of those to the gamma power. So that ends up being pressure at point B was 1.5 atmospheres because it shows it on the diagram right here. And then we multiply by the ratio of the volumes. Volume at B is 0.009. Volume at point A is 0.002. Normally I'd write units, but it's a ratio, so we don't really care about the units as soon as you have a ratio of volumes. And we raise that to the 1.4 power. If you calculate this out, then you should get, as you all said, 12.3 atmospheres. That's part A. And we'll use this again, so let's circle it and remember what we had. All right. Part B says, how much heat enters this gas per cycle, and where does this happen? For part B, we're going to be using this equation here, except that we need to do some calculations first. We know what the number of moles in this case is. It gives us that the number of moles in our problem is 0.25 moles. And CV, I said we could calculate from this right here. Let's see if there's enough room to do that over here. R is 8.31. And we're dividing by gamma minus 1. Gamma is 1.4, so gamma minus 1 is 0.4. And what I got was 20.75 for this. It has the same units as this right here, but kind of running out of room here. So 20.75, do you all agree with that? Okay, so that's our value for CV. And what we're missing then is the delta T's, right? So in order to do this, we need to figure out the temperature difference, but we also need to figure out where is this happening? How much heat enters the gas per cycle and where does it happen? So ultimately what that means is you kind of need to find out what the temperature at all three of these points is right here. Although from the discussion earlier in class today, you should probably be able to guess that this is the process right here where the heat is entering the system. Because it's a constant volume process, but the pressure is increasing. So if the pressure is increasing but the volume's not changing, there's really only one way that can happen, right? You know, imagine a container and it has a gas inside of it and you notice the pressure is increasing but you don't know why. If the volume doesn't change, the only way that can happen is if it's being heated up, basically, right? So it has to happen between C and A. So that means we need to find out what the temperature at C is, and we also need to find out what the temperature at A is. Let's do the temperature at C first. So for this, we're going to use the ideal gas law. We're going to say the pressure at point A times the volume at point A, and we divide by the number of moles of gas times the, so this is just a, TC. I'm doing TC first, my bad. we'll need TA as well, but so TC will be pressure at C times volume at C divided by N times R. We calculated the pressure, or we're given the pressure at point C as 1.5 atmospheres, except we can't use atmospheres unless we're going to change the R constant here. We're given volume in meters cubed, so what I did was I just said, if I take 1.5 atmospheres, we multiply this times the number of, so 1.013 times 10 to the 5th pascals per 1 atmosphere. So that's our pressure, and then we multiply by the volume at point C. The volume at point C is 0.002. And now we do need to write units, meters cubed. We divide this by N, which is 0.25 moles, and then times R, which is 8.31 joules per mole Kelvin. Now, Kelvin's in the denominator, it'll come to the top, so that'll give us our unit right here. There's pascals, which is newtons per meter squared. Newtons per meter squared times meter cubed is going to give us just Newton meter. Newton meter is a joule, so that cancels out with the joules. Moles cancel out, we're left with just Kelvin, so we know that we've properly done our units here. It's always really good to check your units in problems like this, especially when they're units that are unfamiliar to you. So our answer is going to be in Kelvin, and what I got was, this is probably where our answers differ a little bit. For TC, I got 146 Kelvin. Do you all agree with that? Okay. And then for TA, you can do the exact same thing. The difference is that we just need to replace PA and VA. Oh, see, this is where I may have actually made a mistake. No, the volumes are the same. What I did, I just did it like this, basically. I said TC should be equal to TA multiplied by 12.3 atmospheres divided by 1.3 or 1.5 atmospheres. Does that make sense? You're going to be doing exactly the same calculation, except you're just going to replace the 1.5 atmospheres with 12.3 atmospheres, right? Everything else is the same, because the volume at point A is the same as the volume at point C, and the number of moles is the same, all that kind of stuff. So you can either just do the same calculation and plug 12.3 in there, or you could just say, well, I just do this ratio. And then I got basically, well, let's write it as 1200 Kelvin. Now, does everyone agree with that? Is it 1200 Kelvin? I easily could have made mistakes on this stuff. And I'm pretty sure I must have somewhere, because you guys got slightly different answers than me. Okay, good. All right, so we're still trying to find part B. We haven't finished part B yet, because the question was how much heat enters the gas per cycle. So now is where we can take these two numbers and we can plug them into our Q equal to NCV delta T equation. So this will be 0.25 moles. I hope I have enough room here. Times CV, which we said was 20.75. Here I can write the units, joules per mole Kelvin. And then we multiply by our temperature difference. Delta T is always going to be related to the direction. It'll be TA minus TC in this case. So we'll be doing 1200 Kelvin minus 146 Kelvin. It's kind of off screen there, but I think you guys can see what you need to calculate. For this, what I got was I really should be calling this QH, right? Because this actually is the QH. It's the Q from the hot reservoir that's coming into our system. What I got for this was 5465. If you use those numbers that I have, do you guys get the same thing? I'm gonna do it again just in case. So it's 0.25. Oops, I messed that up. Oh, 5468 actually is what I get when I use those numbers. Why did I do that? All right. everyone kind of agreed that it was 5,500 there, right? And technically, in this problem, there's only 2 significant figures, right? No, 3. There's 3 sig figs. So it should be 5470 or something like that. Okay, there's a lot of rounding going on here. It depends on how much you rounded this number off, how much you rounded this number off, right? So it's understandable if your third digit here is not the same as mine, or even if your fourth digit, but as long as you think it's about 5470-ish, that's probably fine. Okay, so that's our answer for part B. Had to do a little bit of preliminary calculations to figure that out. We need to know the temperatures. We also had to convert gamma into CB. So don't forget how to do this, because I'm sure it'll show up in your homework. So that's part B. Part C says, how much heat leaves this gas in a cycle and where does it occur? First of all, we know there's no heat that leaves through this process because it says that it's adiabatic. So we know that the heat, well, we would say the internal energy, it doesn't change from A to B. So it has to be from B to C. And really the only thing we need to calculate then is what is TB equal to. So if we calculate what TB is going to be equal to the temperature here is related to the pressure here, which will be 1.5 atmospheres. Again, we got to multiply by 1.013 times 10 to the 5th pascals per atmosphere. And then times the volume here, which is 0.09. And then divide by NR again. 8.31. And then what I got for this was that the temperature at point B was 658. And then we plug that into the same equation from before. So now we'll call this QC. And QC is going to be equal to NCV times, now it's going to be final temperature TC minus TB. So we can see TC and we can see TB. When I did this calculation, I got negative 2656 joules. And again, let me calculate it again just based on the numbers that I wrote down here. So TC is 146 minus 658. Negative 2656 exactly is what I get for this one. So that's our QC. And then how much work does the engine do? If we have QH and QC, what do I need to do to find the work done by the engine now? If I know QC, which is the energy expelled by the system, and QH, which is the energy that comes into the system, how much work is done by the system? I'll repeat the question. So if I know QH and I know QC, how do I find the work now? You can look back through your notes or what I did earlier in class or however you're following along. Yeah, QH plus QC, that's right. So we just take QH plus QC. And for me, what I got was 2,800 joules exactly. Although now using this, I'm probably going to get something different. So let's do this. So 5468 minus 2656, 2812. These numbers come out just slightly different if you're doing any rounding. So if you're a little bit off, don't worry about it. Just look at the first 2 digits. That's what you should concern yourself with. So this would be the work done by our process. And then finally, part E wants us to find the efficiency, which is really easy. Once you know we've already calculated all the things we need to do this. The efficiency is QH divided by, no, other way around, sorry. It's the work done divided by the energy that came in. So then this is going to be equal to 2812 divided by QH, which is 5468. We don't really need to write units for this again because they're both joules. So if I do 2812, I got about 50%. I still got 50%, so 51% is the efficiency. Okay, that's a good problem. I mean, it requires you to... We had to pretty much use every equation that we derived over the last couple weeks or so, combined with what we learned today about how a heat engine works. And even though most of the equations themselves are pretty simple, it's still a hard problem because you have to infer a lot of information from the picture. The fact that it says ideal gas is obviously really important, and my memory of doing these type of problems, and again, I haven't looked a lot at this textbook, but from doing these type of problems as an undergraduate, doing these type of problems in grad school, you're pretty much always working with ideal gases, like almost 100% of the time, because all the equations that we used here, every one of these equations here is all for ideal gases, right? So just something to keep in mind when you're doing these type of problems. If you're getting lost, never be afraid to rely on the good old ideal gas equation, right? For finding QC, how can we use CV if the volume changes from point B to point C? Hold up. Yeah, you're right. I shouldn't have used that then, should I? That was wrong. Unless it's right for another reason. Let me think about this. Yeah, from B to C, the volume changes. So this should have been CP right here, right? I'm really glad you pointed it out, Kenny. Yeah, so that's wrong. So now we need to put CP in here. Really good point. All right, so let's change this. Doesn't change much, but it absolutely changes the final answer. I'm really glad you noticed that. Very good point. So this should have been CP. And going back up here, I believe that if we know CV, we can just add R to it, right? Yeah, CP is equal to CV plus R. So here, let's get rid of the numbers, because those are the things that are going to change. Okay, so what is this going to be? So this one will change as well. Let's actually plug everything in. So it'll be QC is equal to 0.25 mole. CP is going to be CV plus R, so CV, so that's going to be 20.75. Plus 8.31. And then times TC minus TB. So TC is 146 minus 658. Much, much smaller now. Or larger, sorry. 3719.7. So about 3720. So then check that to tell me if you guys think it's right or not. So then this would be 5468 minus 3720. 1750. That would be the work. This problem is odd, by the way, so if we want to, we can look the answers up at the end. So 1750 joules now divided by QH, which was 5468. It's going to be a lot less efficient now. .32, which is about 32%. All right. Any other questions or comments about this one? What number is this problem? Let's just check to make sure we got everything right. And if we did, we can go back and fix some things. So it's 30.5. Huh. It's not 30. Chapter 20. Okay. It's like, that's Henry's. They look pretty close. Let's see. Here, can I put this like this? Let's do this side by side and see what happens. All right. Ah, that's even worse. I gotta zoom in. All right. So it was 20.5. Okay, 12.3 atmospheres. We got that right. 5470 joules. I think that was correct, right? 3723. Yeah, pretty close. Yeah, 5470 and 3720 is really close to what they got. And then 1750 joules and 31%, 32%. Yeah. Okay. Looks like we got the right answers. Okay, any questions? So one thing I'm curious, because I just haven't done this stuff in a long time, but this feels like it's probably true. Do y'all think we could have figured out the answer to part D by using like calculus? Like, I'm wondering if the work done is equal to the area of this little triangle-looking thing here. Now, it's not really a triangle, right? Because this piece of the curve right here, whoops, this piece of the curve right here is, you know, it's a, what's the word for it? A hyperbola, I guess. It's a, you know, pressure is related to 1 over volume, right? So it's like a. I'm just wondering if we could write an equation for the pressure as a function of volume from the line A to B, and then find the area under that curve, and then subtract the area down here of the box. Do you think that would give us the same answer? Did y'all follow what I was saying? Sounds like it might work, right? It can't be that hard to do. The pressure as a function of volume from A to B is given by... I guess it would be basically this equation, right? Like, okay, let's just zoom out a little bit so we just have some more room to work with here. So according to, okay, there it is. All right, according to that equation, right? P times V, get rid of the ones, to the gamma is a constant. We can calculate what this is because we know what P and V and gamma are, right? Which means that P is equal to that, whatever that constant is, divided by V to the gamma. And then we would just need to take this equation and we integrate P dV between from VA to VB. And then from this, we would subtract the area of this bottom piece down here, which would be basically just, it's a rectangle, right? So then just minus the rectangle. I think that would be equal to the work as well. I think it would. So if that's something you want to try yourself, you can, if you like to do math. Anyway, so it is 12:06. We need to take another break, and then when we come back, we'll talk about refrigerators and the second law of thermodynamics. I hope this was helpful to y'all going through this problem. Just looking at ways in which this might look a little harder on the homework, as it often does. All right, let's take a break till 12:15. A little bit shorter of a break, so that we can cover something decent for the rest of class. Stop the recording.